Hello, everyone, and welcome to today's webinar titled Best Practices for Lot Changes in Quality Control or Reagents. I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is sponsored by Bio-Rad Laboratories. Now, I want to invite everyone to participate by submitting your questions during this presentation. To do so, simply type them into the Ask a Question box located on the far left of your screen and click Send. Any questions we do not answer during the webinar will be captured and responded through the Q&A list that will be posted next week in the Event Resources box, which is located below the Ask a Question box. Now, you'll find a short handout with a summary of today's guidelines there, and you'll be also able to download the presentation handouts once the webinar is available on demand. If you have any trouble seeing or hearing this presentation, just submit those concerns through the Ask a Question box, and we will address those issues. Now, as a reminder, this presentation is educational and offers free continuing education credits. So click on the Continuing Education Credits tab located on the top right corner of your presentation window and follow the process to obtain those credits. So let's get started. Today's webinar on best practices for lot changes in quality control or reagents consists of two presentations and a Q&A session at the end. The first presentation will focus quality control lot changes. So today I now present today's first speaker, Mr. Nico van der Pol. Nico works as a scientific and professional aid affairs manager at the Quality Systems Division of Bio-Rad Laboratories in Irvine, California. He studied clinical chemistry in Belgium and worked both the diagnostic and research laboratories before he started at Bio-Rad. Nico works to promote an understanding of laboratories regulation and best practices as they pertain to QC and EQA-PT programs. For a complete biography of Mr. van der Pol, please visit the biography tab at the top of your screen. Nico, welcome. You may now begin your presentation, sir.
Thank you, Susie, for that nice introduction, and good morning to everybody. Welcome to this webinar on best practices for lot changes in quality controls or reagents. So just to introduce the learning objectives, so hopefully after today's presentation, you will be able to identify how you can establish the new mean and standard deviation for your new lots. You will also be able to describe the new simplified CLSI C24 guidance to perform the crossover studies. And you will be able to explain how to use QC and patient specimens to verify the integrity of a new reagent lot. So for the first part of the presentation, I wanted to talk to you how to perform the quality control crossover studies. So we all know that when we're running quality controls and we have all our different products available in the lab, unfortunately, they don't last forever. So there's expiration dates and there's a time that we're going to have to start with a new lot. The manufacturer makes the new product. And again, same thing there, because there's sometimes up to 100 analytes in a control. The targets cannot be the same exactly every time. So we need to establish the new targets again. We need to know what should be our range that we can accept. And we need to do that for each of these different lot materials. So when we look at QC crossover studies, we'll take a quick look what the current process is, what most labs are still doing today. And then we have the question, can we simplify this crossover studies? And I've based a lot of this presentation on the CLSI C24 guidance, the fourth edition. And so that is the statistical quality control for quantitative measurement procedures, principles, and definitions. So if you would read that document, you would find a lot of these things, a lot of these guidelines, and I just put them a bit together and made it a bit easier for us to follow through. So if we now take a look at what we currently do for our QC crossover studies, so what you see here visually is that we always have to establish our own mean and standard deviation for a control material. We need to do that in the lab because every instrument is different, every procedure that we work on the instrument is a bit different lab by lab. So that means that our new lot of control material should be analyzed in parallel with the lot of the control material that we currently have in use. And for today, and what I hear most in the labs, is that every has that magical number 20. So what we normally do is over 20 days, we collect 20 data points of results. So we still use our current lot in use to do our evaluation of our instrument. And then at the same time, we start running our new lot. Once we get to 20 data points, we then normally calculate the mean and the standard deviation from those 20 data points. And then we move forward with that data so we can continue and we have that data established and we have a valuable mean and standard deviation. It's very difficult and almost impossible to say, okay, today I'm ending with my current lot, tomorrow I start with a new lot, but I just start like that without any information. Then your first result that comes in is an unknown. What if that first result was a failure or was something that wasn't really in control? We would never know until maybe 1 or 2 days later. So that's why we established those targets. So let's break it up. And so we have two things. We have our mean and we have our standard deviation. So let's start on how we can determine our new standard deviation for our new lot. And it's actually pretty easy to start with that, because what is the best standard deviation to use? That is actually our current standard deviation that we've measured over an extended period of time. So our current lot that we've been using for a year, maybe a year and a half or 2 years, that is actually the best possible estimation of our imprecision of our system, because it includes a lot of the events that can influence our imprecision. And so I listed a couple of them here. For example, that could be different operators, environmental factors like temperature, humidity, reagent and reagent lot changes, different calibration cycles, even calibrator lot changes might all be part of that. And also maintenance, preventive maintenance, and other things that we do on the instrument. So actually the first part is almost already finished. So how do we determine our standard deviation for our new lot? It's actually, we just take the standard deviation of our previous lot. So that is really simple. We don't really have to calculate that standard deviation anymore from 20 data points. We just take the current one because that's actually a lot better and a lot more stable and reflective of the performance of our instrument than when we would calculate something with just 20 data points from our new one. So that's the first part, but I also want to give you some more tips and tricks here on what we have to do with that standard deviation and what we have to be careful for. So one of the things that I wanted to show is that when we talk about the standard deviation is always expressed as an absolute value. And when our new target mean is close to our current target mean, then you could take your standard deviation as an absolute value and move that over. But if that target changes a little bit, we have to be careful that we don't use the standard deviation, but it's actually then better to use our coefficient of variation, or CV, to fix that new imprecision target. And so I put an example in here. So you can see on the left, if our current control has a mean of 120 units, whatever they are, with a standard deviation of 5, so then we calculate that that's a 4.16 CV. So if our new control material has a mean of 142 units, if we would just copy over the standard deviation of 5, we're now actually changing our targets. We're changing our CV to 3.52. So what actually happens is that by moving over our current standard deviation as an absolute value, we would be setting a different imprecision target. And that's not really what we want, because we want to make sure that we have the same. So it is better to copy over that CV value of 4.16, and then we can recalculate the standard deviation. And so here, for this control, if our new control material would be at a mean of 142, it would be better to change our standard deviation to 5.9. So that's the first one. What is also important is that sometimes you might have control materials that don't last very long, that have a shorter shelf life, maybe only a couple of months. And when you then want to use the standard deviation or the CV from that one control material, it isn't that strong because it's a shorter period of time. And there is actually a formula, and this is this pooled formula, where you can take standard deviations or CVs from multiple previous lots, and you can combine them together to calculate an overall standard deviation or CV. And so this is this pooled formula. The most important part for this pooled formula is that we have the number of data points which are part of this pooling, because otherwise, if we would just be taking our mean of multiple lots, it could be that a lot that was very short would have an influence in changing our standard deviation. So this is why we have the n in there, or the number of data points that are in there. So using a pooled standard deviation formula can help us to get a better long-term estimate of that standard deviation. Another thing that sometimes can happen is that throughout the life of a quality control, sometimes we might have a shift or a trend or something that changes our targets a little bit. And I put in here a Levi-Jennings chart that shows you that somehow here there was a reagent lot change or a calibrator lot change, and our targets shifted up a little bit, so they're a bit different. Well, if you have something like that, it is also interesting to use that pooled formula, or to maybe just use one part of this imprecision target for this formula. So I show it to you as an example here. So for example, here you see on the left in that blue window that we had a reagent lot A, which had a mean of 50 units with a standard deviation of 1. So that comes to a CV of 6.6%, and we had 100 data points. And then we changed to a reagent or a calibrator lot B, and our mean changed a little bit. So you can see that our target went from 15 to 17. And so now we're at a standard deviation still of 1.1 and a CV of 6.5. So you can see that the instrument still works at the same imprecision. We just have a little change in that target. And we had 150 data points for that latest lot. So if you would take all these data points together, 250 data points, and calculate the standard deviation or the CV, you would actually get a standard deviation here of 1.44 or a CV of almost 9%. So again, what you would see is that although the instrument works at 6.5, 6.6% CV, by having that shift, we can actually get a different SD or CV, which would increase our target or limit. And so that would be dangerous to miss significant changes. So using a calculated or a pooled SD will give you that value of 1.06 or a CV of 6.5, which is the target we want to keep using. Here you could also use actually the CV of, for example, the last part of our lot, that lot B, that 6.5, that would work too. So another suggestion is don't use the insert value range or any analytical performance specification as your own working standard deviation or CV. When you look at insert ranges, they are based on a population of instruments, and they are too wide normally for an individual instrument. So if you look at an insert and you find your target and your ranges there, that is where your mean that you establish in your lab should fall. It should fall within that range. But then you should use your own standard deviation to protect that value or to control that value. And I've seen several labs where they would look at the insert, for example, and the insert says, okay, my target is 100 and the range goes from 80 till 120. Well, if you would take that 80 and 120 as your limits of your ranges, and you would fix that, and now your target would be 90, you are running your control and you find 90 units, then what happens is that on the lower side of your control, you would only have 10 units that you can move, but on the top side of your control, you actually have 30, which would be probably way too wide, and you would have significant statistical changes going up that you wouldn't detect if you would just use those insert ranges. I've also seen labs that would take both ranges and then look how much difference there is between the target and the upper and lower range. And then they would divide that by 2 or by 3 and fix that as their standard deviation. Again, that should not be how we set our standard deviation ourselves in the lab. We should use our own instrument standard deviation and establish that value and use that value. Analytical performance specifications, targets like biological variation or CLIA limits, they are clinical performance targets most of the time. And so using those might give you a feeling of being in control and having good performance, but often they're a little wider. And so they might be missing statistical relevant changes. So most of these analytical performance specifications are there to help you when you have a failure on your instrument to see if it would also affect the clinical performance of your instrument, of your results. And they're not really there to be used as a target by themselves. So there too, again, use your own standard deviation or your own CV. Also, don't use an interlab comparison group standard deviation. So that is the same thing as we discussed. Peer group standard deviation, they will reflect the variation of all the participating instruments combined, but there's also a bias component in there. And that doesn't reflect the individual instrument performance. So I made another example here in that blue area. You can see 3 labs that participate in an interlab program. They all send in 20 data points, but you can see that their targets are a little different. So the first lab finds 105 milligram per deciliter, then 115, and the other one 120. But they all have the same standard deviation of 5, so you can see that their CVs are very close to each other. If you would put these 3 labs together in one peer group, what's going to happen? Well, you can see here that the mean of the peer group would be 113, but that standard deviation is 7.9, almost 8, or a CV of 7%. So again, you would see that the CV of the peer group is wider because you have that variation of those different results in there. So again, you wouldn't be using that 7 as your target, but you need to use your own target, which would be here like a 4.3 or a 4.7 from each of those labs. There is a place in your Unity reports, your Unity interlab reports. There is one report which is called the Statistical Profile Report, where you can actually go see all the distribution of those individual CVs of all the instruments participating. And that is something which could give you some information and some guidance on, okay, how well am I doing? Am I nicely finding the same CV as the other labs, or am I a bit better or a bit worse? But again, it isn't the aim to use that as your target, but it can give you information of how all your other participants in your peer group are performing. So it can help you a little bit, but again, establish your own target in your lab. So that was for the standard deviation. So actually, I gave you a lot of tips and some guidance there, but it's pretty straightforward for your standard deviation. We just use whatever we already had for our existing material. So now we're moving forward. Now we have to establish our mean. We need to establish our target. What is our correct value? And so there, again, according to the CLSI guideline, it becomes a little easier because we can use 10 measurements on separate days. So not the 20 anymore, but just 10. And if you do 10 data points on 10 days, try to include a calibration event or a couple if you can, because also those are the points that introduce a little bit of that variation for your results. Also, try to use the same QC vial frequency as in your daily routine. So sometimes if you would just have to do 10 measurements, you would probably just use 1 vial of QC material and run that for 10 days. But if throughout the day, if throughout your normal routine, you would normally use more QC, or you would be running it on other instruments, and so normally every 2 days, for example, you would be using a new vial, then try to do the same thing for your crossover. For some of the controls, for example, a lyophilized control where you have to do a reconstitution, that is important that you see a little bit of that variation while you're doing your crossover. So try to mimic that, that routine, that daily routine. Also, make sure that if something happens with the instrument and your current lot is showing you that there's an out of control condition, then don't accept the new lot result. So reject that and just add one more data point once the instrument is back in control, or just do another one the next day or go a day longer to establish your crossover for that. Again, as a couple of pointers, like we also said for the standard deviation, don't use the insert value. The insert value are provided as a guideline, and you should establish and verify your own targets. Why is that important? Because you have to make sure that when a target is set by a manufacturer and other laboratories that help you to set that, often they will be using a different reagent lot or a different calibrator lot. So those targets might always be a little bit different. So make sure that you establish your own target by yourself and don't just copy an insert target value. If a target value needs to be established more quickly, if you're running out of other material, you're a little later, you could also go and do a couple more results a day. But remember, the more you speed that up, the more you're starting to remove the variation of those different steps in there, and that could give you an optimized or a little better target than you would want. But for the mean, actually, it is less of an issue than for the standard deviation. So you could speed it up a little bit if you would want. Again, just make sure you plan everything out nicely. Make sure you have your 10 days to run your new lot. Another one, don't use the interlab comparison peer group mean. So again, it's the same thing like I already said before. These values aren't really an individual instrument value. So as you can see here on that little distribution chart, it is a normal distribution of results that comes in. Not every instrument has exactly the same result. And it doesn't mean that you are more correct or you are less correct if you're a little bit next to that target. If your peer group is 120 and you're at 117, your instrument can be working perfectly fine and correct. And then you just use your 117 as your target. The interlab group is made out of sometimes hundreds of instruments distributed across the world, and they can all have different reagent lots or calibrator lots, and so they don't really reflect your pure target, but they are different variations. So finally, if we look at that crossover, then we can actually now see that this is like a summary screen I made to show you what you should do when you're doing a new quality control crossover. So you can see on the top, we start with our current lot that is in use. And so we have our mean, our standard deviation, and our CV. And then 10 days before the end of that lot, we're going to start measuring our new lot. And we measure one data point every day. And once we get to those 10 days, what we're then actually going to do is from those 10 points, we calculate our new mean for our new lot. So we calculate our mean B here. And then we take the CV of the old lot. And with that CV, we can now recalculate the standard deviation for the new lot. And then we're ready to go at day 10. We now have our new standard deviation, our new mean, and we can start evaluating those values. Remember that they're always an estimation of our targets because we only had limited amount of data here. So it's always interesting to reevaluate the mean and the standard deviation in the following months after we collect more data to see if it still reflects the actual performance of the instrument. What can also be said is that if you're using multiple instruments, if you're a bigger lab and you have 4 or 5 instruments, and you use the same target on those multiple instruments, then it is actually very good and actually almost better to also measure your new mean on those different instruments. So what you would do, for example, is that you could then run one quality control a day on 4 instruments for 3 days, for example, and that will give you 12 data points. And those 12 data points would be enough to have your mean set. Just as a little tip, always make sure you measure at least 2 QC points per instrument, just to avoid if there would be anything going on and you would have some strange results. Just make sure you have 2 points per instrument so you can catch a flagrant outlier or something like that. And as last couple of slides, I just quickly wanted to show you, if you use a QC data management software like Unity Real-Time, how you practically can do a crossover study in the software. So here you can see a duplicate lot screen for Unity Real-Time. And that means that when you're running into the end of a lot, you can actually tell the software, okay, this is my new lot. You define it here, the new lot number. And then you have an option in the bottom to copy the fixed standard deviation over to the new lot. And in our software, it should actually normally say fixed standard deviation / CV, because it copies over whatever you had fixed, either standard deviation or CV. So then when you do this, you will see now in your layout that you actually have your two lots in the software next to each other. So you have your old current lot and you have the new lot underneath. And when you then go to your fixed mean and your standard deviation screen, you can see in this new lot that the mean is empty because we don't have any data yet, but you can see here that for level 1, the CV was copied over. For level 3, the SD was copied over. And I just did that as an example to show you that it copies over whatever you had set in the software. The best one is, like we said, the level 1 is that we copy over the CV, because then we don't have to worry about the difference in absolute values. So when we go to the next screen, after our 10 data points were collected, we can now ask the software to calculate from the floating statistics to calculate our mean, and that mean is then applied, and now you can see that our table is completely filled out. We have a mean, and then we have a standard deviation and a CV fixed, and we're ready to go with our new lot of our quality control. If you want to visualize that, you can use a multiple Levi-Jennings screen. You can see here on the top, you see the current lot. On the bottom, you see the new lot that's expressed, and that blue area shows us where we were doing our crossover study. You also have an option to put these two Levi-Jennings together into one chart. And then here in blue, you can see the crossover. Here I had to change the colors a little bit because otherwise it is a lot of lines together. So here in blue and green, you can see the new lot. And then the other purple and orange was our current lot. So like this, you can nicely see that now normally we'll continue with those new lines with the new lot, and the old lot is discontinued. We stopped using that. So far, this was the presentation on the quality control crossovers, and I'm going to hand it back over to Susie for the second part of our presentation. Thank you.
Thank you, Nico, for that informative presentation. We will now start the second presentation of the webinar, which will discuss reagent lot changes in the lab. I now present today's second speaker, Mr. John Pacheco. Mr. Pacheco performs research in quality control and patient risk issues for the Informatics Discovery Group at Bio-Rad Laboratories in Plano, Texas. John has had the opportunity to collaborate with laboratories around the world, developing practical real-time interlaboratory controls and proficiency testing systems. As an innovator, he has developed numerous ideas leading to over 35 laboratory-related inventive patents around the globe, all providing new and cutting-edge solutions for diagnostic laboratories. For a complete biography of Mr. John Pacheco, please visit the Biography tab at the top of your screen. John, welcome. You may now begin your presentation, sir.
Thank you, Susie. I appreciate that introduction. Howdy. So I'm here to talk about what do we have to do when we change reagent lot numbers. And along the same lines, that's called the reagent crossover study. Unfortunately, reagent crossovers are a little bit more complicated than when we do a QC crossover. And we'll talk about why that is. But it's a very, very important activity that you make sure when a new reagent lot number is introduced to your laboratory that it doesn't cause problems. one of the reasons for that is actually you want to avoid unfortunate circumstances like what happened here in this news article, where a new lot number of reagent actually changed the behavior of the test method to the point where it was affecting the actual diagnosis of patients. And this is just an example of how critical it can be when you change lot numbers. You simply have to make sure that that change doesn't impact either the way that your test method performs for patients or the way that it works for controls. So the bottom line is that reagent systems are a critical part of the test method. And usually, as long as the lots are stored according to manufacturer specifications, they're stable until the expiration of the lot. But when you have a new lot number, it needs to be evaluated to make sure that there aren't any issues that can affect the performance of either patient specimens or QC materials. And so that's why we do a reagent crossover study, is to make sure that we've evaluated, any possible performance changes. So one thing that can happen is a change that takes place that affects the QC results, but not the patient results. This is called the matrix effect. And that's why we need to, when we change reagent lot numbers, we need to take a look at what's happening with the patients and specimens, and we also need to take a look at what's happening with the QC, because we can have circumstances where only the patient specimens are impacted, or only the QC specimens, are both. And so when we design reagent crossover studies, we have to take a look at what's happening on the patient specimen side and what's happening on the QC side. So how do we do this? Well, fortunately, there is guidance that's available. And so what I'm going to be talking about for the rest of my talk here is how do we use the CLSI EP26 reagent crossover studies. It's user evaluation of between reagent lot variation. So this study describes in detail exactly how do you design a reagent crossover study. And that goes into what do we need to do to ensure that we are comfortable with any changes that would take place on the performance for patient specimens, and make sure that we're okay on the performance of QC specimens. So, unlike what we have on the QC side, we have to actually design a reagent crossover study. So it's a little bit more complicated because we have to go in and determine just how many specimens, how many samples do we actually need to take a look at. As Nico told us, when it comes to QC studies, you can use 10 samples collected over 10 days, but that's not the case when it comes to reagent crossover studies. So what we need to do is take a look at both patient and QC samples that are evaluated when we have on both the old and the new system. And so what we want to figure out is, okay, how many specimens are needed, and how do we judge whether or not we're going to accept the results? And that's where we have the guidance that's coming from CLSI. So, fortunately, if somebody has done a reagent crossover study, we can actually use their results. So unlike the scenario when it comes to a QC crossover study, that has to be done for each laboratory. But if we have an affiliated laboratory that has done a reagent crossover study, we can actually use their results, and we don't need to take a look again at the patient side. So we still do need to take a look at the QC side, but at least we can reuse the results from somebody else that has actually done a reagent crossover study for that specific lot. So one of the things that we need to do is determine exactly how much of a change can we tolerate. This is called the critical difference, and that tells us just what is the limit of change that we're willing to accept. So it's kind of similar to a total allowable error or a quality specification. And the critical difference values, they may come from a number of different sources, like biological variation or state of the art or expert opinion. But part of what needs to happen is that you need to determine just how large of a shift would you accept with respect to the new and the old lot number. This is called the critical difference. It's abbreviated as CD. Well, once you have the critical difference, so part of what you also have to do is you need to have the within laboratory imprecision, which is abbreviated as SDWRL, and you need repeatability. So these are values that you can obtain from doing a precision study. And normally, once you do a precision study to determine these types of values, you can use them from lot to lot. So we tend to attribute these values as a characteristic of the test method. And so once you've derived them, you can reuse them. And so both of these, the within reagent lot standard deviation and the within laboratory imprecision, they are concentration specific, but those need to be computed before you can actually go in and do reagent crossover studies. So one way that you can determine a critical difference is using the biological variation approach, which is based on a reference change value. And so if you're familiar with how to compute a reference change value, you can do something very similar using the same approach, except for the critical difference. You would use the within reagent lot standard deviation. And so that, as an example here, if you have if you've got a within CV of 6 and a within reagent lot CV of 1.6, you can compute a critical difference as 17.2. So if we've got then the critical difference, and now we've computed just how much of a difference are we willing to accept from one reagent lot to the next, let's see, how do we actually use that? Well, we need to determine what the rejection limit is going to be. And in addition to the critical, in addition to the critical difference, we also have this concept of taking a fraction of that critical difference and computing the reagent limit. So the rejection limit should be based on the clinical utility of the test. So it's a little bit like the severity of harm category that comes to us from EP23. And so if you have a test that uses a low factor like 0.6 or actually it should be 0.5, and then least critical tests can use a higher factor, which will give you more of a range of 0.9 or 0.8. Okay, so let's take a look at how we actually use these. Oh, sorry. So in addition to determining how large a critical difference we're willing to accept, we're going to take that information and use it to also determine what number of samples are going to be required. And so within EP26, in the appendices, there are a set of tables that allow us to determine how many samples do we need at each concentration. And there's 3 tables for a single concentration, or 2 concentrations, or 3 concentrations. And so based on the number of concentrations that you're using, that's going to determine which of the appendices you need to use to figure out how many samples would you use, and what are you going to need for a given rejection limit. So, okay. Let's take as an example table A2 for 2 concentrations. Now, when you look at this, we can first see that if we look at the columns, there are the first 2 columns here are the critical difference divided by the within reagent lot standard deviation, and then the second table there is the standard deviation of the total, within the laboratory standard deviation divided by the within reagent lot standard deviation. So those are what we use to actually index the row. And then the other columns are based on our rejection limits. So we're going to use 0.9, 0.8, 0.7. And so that's how we select which column are we going to actually use. So let's take a quick look. You need to actually compute those 2 ratios first, where we've got, again, the ratio of the critical change to analytical precision. And basically, the higher that this is, the lower number of samples you're going to need. And then you've got the ratio of your standard deviation within the laboratory divided by the within reagent lot standard deviation. So that's a ratio of repeatability to analytical precision. And the smaller that is, the higher the number of samples that you're going to need. So we use that combination is what's used to index the row that you're going to use within that appendix. Okay, so the way that we do this is you first find the section that matches your CD to SWRL ratio, And then if you have a value that's between two values, you're going to use the next lowest value. And then you find the row that matches your SR to SWRL value. And once you've got that, then you go across to find the column that corresponds with your rejection limit. So the number outside the parenthesis is the number of samples required. The first number inside the parenthesis is the probability of a false rejection, a false positive result. And then the second is the probability of error detection. So let's take a quick look. Let's see how we actually use this. All right, so in this example, I'm using an example based on AST with two sample concentrations. We've got 40 and 200, and you can see the corresponding critical differences. And here we have the critical difference and the SWRL and the SR. And we've decided that for this analyte, we're going to use a rejection criteria of 0.7. And then we've gone on ahead and we've computed the ratios that we need to use in order to actually find within the table just how many samples do we need. So let's look at what that looks like. Okay, now this is a little hard to see, but if you take a look here, the ratios that we're looking for are 7.7 and 0.62. And so when we look this up, we're going to go one down. So that puts us in for the first one. So this is a section of the table. Then we look at 0.62, and so that gives us the row of 0.6, and then we select the column that's telling us, okay, what is the experiment design that we need? And it's telling us that in this case, we need just one sample. Now, the samples that we're talking about here are the patient samples. So for the design of this crossover study for AST, we would need one sample that's going to be near 40. And then we would do the same thing on our second concentration. So in this case, for 200, we go through the same process, and at 4.9, we find the one that's next down, which is 4.5. And then with our SR to SWRL ratio, it's 0.32. So one down from that is going to be 0.3. So we basically round down when we're trying to determine exactly which row to use. And in this case, it's telling us that we need two samples near 200. So that then gives us the sample design. Okay. And then this is what, now that we know that we're going to need two specimens for the higher concentration and one specimen for the lower concentration, this is what that might look like. So we can see that the current lot result, we have 62 for the lower concentration, and then with the new reagent lot that we're looking at, it's 62.6. And so the difference between those is 0.6. And in this case, we want to actually take a look at what's the average difference, and it's 0.6. Then we can do the same thing on the higher concentration, where now in this case, we're using two samples. And with those two samples, when we do the same thing, we see that we have a difference of -1.4 and minus 11. So when we average those, the average difference is minus 6.25. Well, our rejection limits are 7 and 14. So our differences are less than the rejection limits, and so we're going to go ahead and accept those. And so this is how you design the study that you're going to use. And once you have done this type of a study, once you've done the design of the study, you can use this over and over again. So while it does take some initial work to design this type of study, once it's done for your test system, and ideally this is done when you adopt the test system. So when you're doing the validation of your test method, you want to do this design at the same time. But if that didn't take place, well, then you need to do the design. And once you have the design, you can use it over and over again. The only thing that you may need to, when you may need to revisit it, is if you have issues with trying to locate patient samples that are going to be in the concentration range that the study is designed for. So all of this is coming from CLSI document EP26, and that is what I would recommend that you take a look at for determining how to do reagent crossover studies. Thank you very much.
Thank you, John, for that great presentation. We will now start the live Q&A portion of the webinar. If you have any questions you'd like to ask either Nico or John, please do so now. Just click on that Ask a Question box located on the far left of your screen. So let's get started. Gentlemen, it looks like we already have some great questions coming in addressed for both of you. So our first question goes to you, John. Our audience member says, do I really need to use patient specimens for a reagent crossover study?
Yes, you do. And the reason for that is that, you know, as I noted in my presentation, there is this possible matrix effect where the QC specimens can sometimes behave differently than patient specimens. And so you do actually need to take a look and confirm that what is the performance with respect to patient specimens. And unfortunately, you know, we've had reports from labs that, you know, if you simply rely on only QC results, you can have shifts when it comes to the patient means that are caused by a new reagent lot number that you might not detect just from QC alone. And so because of that, you do need to actually look at both QC and patient specimens.
Thank you so much, John. And our next question is for you, Nico. How often do I need to check my mean and SD values if they're still appropriate?
Okay, so after our crossover, when we initially set our targets, then I would wait until we have something like at least 60 to like 90 data points before we would look at them again, and then we can evaluate if our targets are still appropriate, if something would have shifted a bit up for your target, for example. Those are things you can then evaluate. Throughout the life of the control, it is something which you would probably do like in your monthly review. And I really like using the Levi-Jennings chart for that, because you can clearly see if your results start trending upwards or trending downwards, if that would need a change. It's also important to see if you can rather fix it first with, for example, a calibration or with maintenance, than just continuously changing your targets. That is also not the best practice. But normally you wouldn't check more than once a month to see if something is behaving differently. Also remember that, the most critical points are reagent lot changes or calibrator lot changes, things like that, that can have an effect on your targets.
Thank you so much, Nico. And I want to thank our audience for these great questions coming in. We'll move back to you, John. Should we also establish new means for each different QC or reagent shipment?
So what you need to do is take a look to see if that's necessary. So reagent lots, a new reagent lot may or may not require you to change means. And what you need to do is simply evaluate your QC materials on the new lot number and take a look to see if, how different are they from the old lot number. And if they're very different, then you need to basically do the same approach, do another QC crossover if there is a significant difference in the performance.
Thank you so much. Now, Nico, an audience member wants to know, can I establish my mean value in multiple measurements on the same day?
Yes, good question. You can if you would want to, if it's really necessary. With this new guidance of CLSI, with just using 10 data points in 10 different days, it already shortened our crossover study. If you really don't have enough material to last those 10 days, for example, and you need to go faster, you can. Just remember that if you go faster and you do multiple measurements in one day, there could be a bit less variation in those results. So you could have a bit more, you could see it a little later, for example. So you can do it, but just make sure that after a longer period of time, you reevaluate and you look at it again.
Thank you, Nico. And here's a follow-up question about outliers. Do I have to remove outliers from my crossover period?
So I think I mentioned it in the presentation. So we would always look at our current quality control to see if there is something out of control or there is a problem. Then we will remove that result from the crossover study. But it could happen that you have maybe a random error or an outlier just in your new lot when you're doing your crossover study that didn't happen in the other one. So if you would see a clear and flagrant outlier in those 10 data points in your crossover, you could remove it and add an additional data point. So you could take a look. Normally, the chance is smaller to have something like that, but if it happens, you could actually remove it, yes.
Thank you so much, Nico. And we have time for just one more question. John, this one's for you. How can I tell if there has been a change in performance with my new lot of reagents?
Well, that's actually what we have to do here, is that the way we can tell if there is a change, and really what we're concerned about is not just whether or not there's a change. What we're concerned about is there a change that is large enough that it's going to impact the way that we use test results for our patients. And so it's a critical change that we're trying to detect. And the way that we do that is with this reagent crossover study design. So we need to take the number of samples that our design is requiring us to use, and we're going to take patient samples, run them on the current lot number, and run them on the candidate lot number, and then look at those differences and see if those differences are acceptable or not. And so we really want to do that before we actually start using the new lot number of reagents, because if we don't do that check, then we are going to introduce those changes without realizing that's happened, and that can present a dangerous set of circumstances for the laboratory, and in particular, it it can potentially have a negative impact on our patients. And so that's why we actually have to do this reagent crossover when you have a new lot number, if somebody else that has not done that study.
Gentlemen, I want to thank you again for your time today, and I want to thank you for your important research. And before we go, I want to thank our audience for joining us today and for their interesting questions. Questions we did not have time for today will be addressed by our speakers and posted in the event resources by the end of next week. And this webcast will be available on demand in the auditorium from Friday on. If you found this information helpful, please share it with colleagues. For the next webinar on April 7th, we will have a panel discussion where you can ask all of your questions about quality control. 4 QC experts will be our panelists, and they will answer your QC questions. Please stay tuned and watch your email inbox for the invitation, and you will also be able to submit your questions up front to the panel. Until next time, stay safe and stay healthy. Thank you, and bye-bye.